Hi, my name is Erin Villamek. I am going to be presenting my project on portfolio optimization with a genetic algorithm. So quickly to review the agenda, first I'm going to go over the introduction to the problem, literature review, I'll describe the data set I'm using, and then I'll go into the details of the algorithm and then how it was implemented. I'll go over the results and then my conclusions and some future work. So, what is portfolio optimization? Portfolio optimization is just selecting stocks for your portfolio so that you maximize your return and you minimize your risk and cost. This is integral for investment success. Without an optimal portfolio, the returns of investments will likely be minimal or result in a loss. The importance of this decision has motivated many researchers to find a method that determines the optimal stock portfolio. As data science has become more developed, it's provided some powerful ways to solve portfolio optimization. And one of these methods is the genetic algorithm. So genetic algorithms simulate the survival of the fittest among structures. So it applies the concepts of reproduction to data. So this little clip kind of shows an example of how over time, as you go through new generations, they just get stronger, better, more efficient, more reliable. It's an efficient way to find optimal solutions to combinatorial problems. So this project applies a genetic algorithm to the standard & Poor 500 index dataset. Using a snapshot in time of the S&P stock market, the genetic algorithm's objective is to find which combination of stocks will return the best profit. So going into literature review, there have been several studies applied to machine learning and portfolio optimization. I'm just going to go over a few here. So in one example, a study investigated several different methods of portfolio optimization specific to Bayesian optimization, and they determined which method was optimal. So some of the algorithms explored here were Gaussian processes, probability of improvement, upper confidence bound, and hedge algorithms. They concluded that hedging algorithms were a powerful tool in the design of acquisition functions for Bayesian optimization. So another study uses a type of regression to optimize a portfolio. The one they developed was performance-based regularization. This regression sought to minimize variance, and the study concluded that the regression was effective at improving portfolio performance. And then the third study used a genetic algorithm in an attempt to find an optimal portfolio. So genetic algorithms search a space of solutions in an attempt to find the best combination of items, and this study concluded that the genetic algorithm has outstanding advantages over the conventional portfolio mechanism. So this last study was what inspired my project of solving portfolio optimization with a genetic algorithm. However, some of the details between the study and my project are different. One example being the research study focused on optimizing portfolios by diversifying across industry. My project allowed any stocks in the S&P 500 to be included, regardless of what industry they came from. And although just a few studies are mentioned here, there's much more research that has been carried out in hopes of building an algorithm to accurately determine an optimal portfolio. And as contribution to that research, this project takes on the problem by proposing a genetic algorithm as the solution. The data set used for this problem is the S&P data set. It originated from Yahoo Finance, but I just got it off of the DataHub website. It contains basic financial statistics on the 500 companies in the index. Some of examples would be price per share, dividends, and earnings per share. The data set is not a time series, it's simply a snapshot in time. The exact date of the snapshot is not known, but the data was published in DataHub last year. Each record in the data set represents one stock in the S&P 500. This level of detail actually made my job really easy because the genetic algorithm expected one row per company, and the output is one row per company, so I didn't have to do much pre-processing. In this project, the main columns I used were market capitalization and rate of return, which I had to calculate. So the function of rate of return is given by the current price minus the last price point in time, all divided by the last price point in time. But since this is not a time series data set, I didn't have the last price point in time. I did, however, have earnings per share, so I just assumed that that was equal to current price minus the last price point in time. And operating under that assumption, I was able to calculate rate of return. The charts here show the distribution of market capitalization and rate of return by company. So you can see market capitalization quickly tailed off around 100 billion, so most companies are underneath that. And rate of return is mostly positive. There was one outlier that you can see. It had a negative 228% rate of return, but I just left that in for the training of this algorithm. So now I'm going to get into the details of the genetic algorithm, what the different components are, what the overall process is, and each component is coded as a function in my Python code, and it relates to a specific part of this whole metaphor of genetic reproduction. So let's get into it. The first component is a chromosome. Excuse me. A chromosome is simply a feasible solution in the solution space. Since the goal of this project was to find the optimal stock portfolio, a feasible solution is defined as a combination of stocks. A chromosome could have any number of stocks selected as being a part of the portfolio. But to build the initial set of solutions, I limited the number of stocks allowed to 100. Basically, the reason I set this was so that the algorithm wouldn't immediately select all 500 companies and then basically fail to display its effectiveness. I wanted to see the change over time from the very first initialization of the solution to the final solution. To create each chromosome, a random number between 1 and 100 was selected. This number represented the number of stocks to be chosen for the solution, and then once I knew how many stocks were going to be in the solution, I had to choose at random which stocks would be included in the solution. So the way I encoded the chromosomes was each solution is a list of 500 elements, each element representing a company in the S&P 500. And the value of each element was 0 if the stock was not included in the portfolio, and 1 if it was. The next component of the genetic algorithm is fitness. The fitness of a chromosome equates to basically the result of its evaluation metric. For this project, the evaluation metric was a normalized score for all the stocks in the candidate portfolio. The two main features used for evaluation were market capitalization and rate of return. The reason I chose these, first market capitalization, is I read in research that market capitalization is one of the well-known core factors frequently used in analyzing and forecasting the stock market. I chose rate of return to evaluate on because it throws the concept of loss into the overall evaluation. So market capitalization will always be positive, but rate of return can be negative. Even if a company has a very large market capitalization, they could simultaneously have a negative rate of return. So adding rate of return into the calculation helps account for any variability that might occur from only evaluating based on market capitalization. And then to aggregate all of this into one fitness score for the entire solution, I calculated z-scores for both market cap and rate of return for every stock in the solution, and then I took the average of those z-scores so that I would have one z-score per stock, and then I summed up all the z-scores together in the solution, and that was the overall fitness score. So using this calculation, a higher metric equated to a better performance and return from the solution. The next component of genetic algorithms is population. So the term population refers to the entire population of solutions. Part of the genetic algorithm, which I'll get into more in a minute, is to breed two solutions together to get a child solution that's a combination of its parents. So for this to occur, there must be some initial population of solutions to choose parents from. So that's why the component of population is important. The initial population is just created by making a bunch of random chromosome solutions. I chose the size of the population to be 1,000 so that it could be large enough that a big number of combinations could be made out of the initial solutions out there. Next component in genetic algorithms is tournament selection and mating pool. So to determine which solutions will move forward to reproduce, a tournament is held to determine the best contenders. Kind of similar to how two animals battle to determine which one is going to move forward to reproduce. In the code, the tournament selects 3 random chromosomes from the population and then chooses the best one based on its evaluation metric. Excuse me. The best solution advances to the mating pool, where solutions will combine to make new children solutions. In the tournament selection, repeats are allowed. So what this means is that the same solution could show up more than once in the mating pool if it were randomly chosen more than once and it had the best evaluation score each time. The resulting mating pool from the tournament is the same size as the initial population, so 1,000 solutions in total. Next component is crossover. Crossover is the process of creating new children solutions from existing parent solutions. So 2 parent solutions are the inputs to the crossover function, and the output is 2 children solutions. Crossover occurs conditionally in the algorithm, so it only occurred with a 90% probability for the project. So what that means is I randomly generated a number between 0 and 1, and if it was less than the crossover rate, which was 90%, then crossover will occur. Otherwise, the algorithm just skips to the next step. So how crossover works is it chooses a random point in the solution to split. So your solution is a list of 500 elements. Somewhere randomly in that list is where it's going to split, and that's called the crossover point. Then 2 parents are merged together by taking the front portion of one solution and the back portion of another, both separated at that crossover point. This is repeated twice, and then after it's repeated twice, you have 2 children solutions, and those are what's added back into the total population of solutions. The next component of genetic algorithms is mutation. So after child solutions are generated, mutation basically just means the solution, like one solution gets randomly changed. That also occurs conditionally, similar to crossover, although mutation occurred with a 10% probability, so it happened much less often than crossover did. If mutation did occur, it occurred by means of one flip mutation. So what this means is a random stock in the solution, the value was flipped from 0 to 1 or vice versa, depending on its value. And then that mutated solution was returned to the population. So once you go through all of these steps, you have more than 1,000 solutions, and the genetic algorithm takes the top 1,000 solutions after the end of all this process, and those 1,000 solutions is what goes on to the next step, and the process repeats. So here's the overall flow of the algorithm. You start by initializing your population and creating random solutions. Then you step into your loop, which is determine the mating population by tournament selection. Then you generate offspring through crossover and mutation. And then you filter the population down to contain the top 1,000 solutions based on its evaluation metric. One thing I haven't touched on yet that I'll explain more is the variable generations. Basically, that just means how many times you iterate through this process. So if you have not hit your cap, you'll go back and you'll do the mating pool again. If you have, then you move on and you retrieve the chromosome with the highest evaluation metric, and that's the optimal solution. So now I will get into how this was actually implemented and what the results were. Several hyperparameters were used to conduct the genetic algorithm. They're summarized here in this table. I think I've gone over all of them, except for generations, which one more time is just how many times the algorithm iterated. I set it to 5,000 because I wanted it to be large enough for the solution size and the portfolio combination of stocks to change significantly. Using these hyperparameters, the genetic algorithm was iterated through 5,000 generations. This problem is a combinatorial problem, and if you think there's 500 possible stocks to be included in your portfolio, so the total search space of this function consists of about 9.3 times 10 to the 157th power of total solutions. That's pretty big, and as such, it's not really a surprise that it took a while to run. So on my personal laptop, running 5,000 generations of this took about an hour. Getting into the results, the optimal solution resulting from the genetic algorithm was 475 stocks out of the total 500 in the S&P. It's worth noting that the number of stocks in the solution is much higher than the limit of stocks allowed when creating the initial solutions. And this is because once the initial population was created, crossover occurred to create new solutions, and I didn't enforce that 100 cap limit to the crossover function, although it could have been incorporated. And since crossover takes a random combination of both parents, the resulting child solution can have more than 100 stocks in it. I expected this algorithm to run pretty well, and as expected it did. You can tell by the bar charts here. They show the top 20 stocks in the total S&P 500 and in the optimal solution for both rate of return and market capitalization. And in both cases, the same stocks show up in the top 20. So all of the well-performing stocks are included in the solution. The overall performance of the algorithm besides this was better than the S&P 500 as well. The average rate of return was 0.5% higher, and the average market capitalization was $1.4 billion higher. This table just gives an idea that across the board for the different financial variables that the optimized portfolio is performing better. Some future work that I would like to do is to further develop the idea of limiting the number of stocks in the solution. So for example, if I have $10,000 to invest, which stocks should I choose, and also how much of each stock should I choose? I think that would be a cool way to incorporate cost. Another idea would be to consider and incorporate the industry diversification idea that I read in the research paper. And then finally, I would like to continue tuning the hyperparameters to get the best results. So in conclusion, using a snapshot in time of the S&P stock market, a genetic algorithm was implemented to find which combination of stocks would return the best profit. The genetic algorithm consisted of initializing a population of solutions, breeding the solutions together to create new children's solutions, performing random mutations, and then determining which of the resulting population was the best to move forward. The genetic algorithm was implemented over 5,000 generations to find an optimal portfolio of 475, and the optimal portfolio did have better market performance overall compared to the entire S&P 500. In the future, further tuning and modification to this algorithm could help drive portfolio optimization across the market. Genetic algorithms are a powerful tool, and this project has proved that it has a strong potential for successful applications in portfolio optimization. Thank you.